Hello, everybody, and welcome back to Markov processes. I have a lot to do so that you can work on your homework. So I'm not going to spend time taking questions today, unfortunately, but on problem one, you're asked in parts A and B if the thing is a Markov chain, and you can give an English language explanation. You don't have to prove it by writing out lots of conditional probabilities. So that's fine. And actually, you're already able to do 1 and 2. 3, we're in the middle of. You're already able to do 4 and 5, and we're going to cover 6 today. So let's get going. I am going to share my screen. Why do I announce that every time? I don't like to announce it, but it takes up some of the dead air when I'm sharing my screen and no one is saying anything. By the way, I will see some of you in the classroom on Monday. We are in ECCS 1B12. If you are registered for a remote section, you probably shouldn't come on the first day, but I imagine because everyone will always be able to watch synchronously the broadcast from the room and also videos, I imagine we're not going to be full. And that's really what the issue is there any room in the room? So for the first day, let's just see how much we fill up. Okay, so we were in the middle of an example. I may not have the exact same numbers as last time because I don't remember what they were and I didn't feel like looking at the video. But I had an assembly line that produces widgets, and we had some raw materials. Last time I said it was copper wire, and the raw materials sometimes cause the widgets to be defective. And I was trying to make some case about impurities in the wire, being sort of in contiguous pieces of wire that could affect uh, consecutive widgets. So there are two possibilities here for the widgets, good or defective, and I'm going to call them G and D. And here are the rules. Okay, so this example is in the notes, but I'm not sure if I use the same numbers. So if the last two widgets were defective, the next will be defective with probability 0.4. If the last two widgets were good, the next will be good with probability 0.95. If the last one was defective, but the one before that was good, the next will be defective with probability 0.3. And if the last one was good, but the one before that was defective, the next will be good with probability 0.85. And I guess I should have started with like a topic title. What we're doing right now is trying to put a longer history into a Markov framework. So not very long, 2 days. And so to do that, and this is very much like, let's bring the homework up. This is very much like problem 3 on the homework. So what we're going to do is group days into groups of 2 days. So we're going to look at states, like good, good, defective, and so on. There's 4 states. And we're going to put together a probability transition matrix for these states. So I need to go from, all right, this is the way I would write them as ordered pairs, but because it's slow to write them this way, I think I'm just going to write like letters like good, good, defective, good, and defective, defective. So that's how I'm going to write those 4 things above. And then we have to go to good, good, defective, good, defective, defective. So the way we do this is realizing that there's always overlap here. If I didn't actually define a chain or anything, but if I did, and I don't want to, so I'm going to write something and then erase it. But if I did have like a chain xn being good or defective, depending on the widget, the nth widget to come off the assembly line, we're looking at something like putting them together like this. But I'm not giving names to these. So there is overlap, yn and yn plus 1. This would be xn and xn plus 1. So there's always an overlap there. And so for that reason, well, let me start with one of the entries of this matrix. The good, good to good, good is really just 3 widgets. And we're going from here to here. So if you go back to the rules, we had a rule that said, this is kind of the day we're trying to predict. If the last 2 were good, the next will be good with probability 0.95. So that's why I'm going to put a 0.95 right here. And the next state in here is really like good, good, defective. So we're going from good, good to good, defective. So this is like good, good to good, defective. And if the last 2 were good, the next one will be good with probability 0.95, meaning it will be defective with probability 0.05. And the other states in this row just can't happen because like good, good to defective good is really supposed to be an overlapping day. These need to be the same if you're going from this state to this state. So those probabilities are going to be 0. And I'm going to go ahead and put in the other zeros right now. For example, good defective, the first letter of the next state needs to be defective. So the first 2 entries here, the good, good and good defective, have 0 probability. For the next row, the defective, come on. For the next row, defective good, right? We've got 2 days and then 2 more days and overlap in the middle. So the only ones that are possible are states over here that start with good. So I have a couple of zeros over here because I can't end in good and start in defective. Okay, and finally, defective, defective, I can't move to good in that step. And so let's fill the rest in. Rather than trying to go through each empty element here, I'm just going to go back to the rules and fill in what we know. So the first rule was if the last 2 were defective, the next will be defective with probability 0.4. So that corresponds to like defective, 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 or going from defective, defective to defective, defective. So that corresponds to this entry of the matrix, and that's where I'm going to put that 0.4. And then a lot of this is zeroed out. So this other one, the row has to add up to 1. So this is going to be 0.6. And let's look at, let's see, if the last 2 were good, or we have that one taken care of. So the third rule I had was if the last one was defective, but the one before that was good, so good defective, the next will be defective with probability 0.3. So that's going from good defective to defective defective. And in my matrix, that is over here, 0.3. And so I can fill in that row and put in a 0.7. And finally, if the last row was good, if the last widget was good and the one before that was defective, the next will be good with probability 0.85. And this is kind of a mess here. So if the last one was good and the one before that was defective, that's this state, the next will be good with probability 0.85. And that really corresponds to moving from defective good to good good. And so in my matrix, that is right here, and that's where I'm going to put the 0.85. Okay, so now that we've made a kind of 2-day history Markov chain, let's answer a couple of questions. We won't spend that long on this example. It's really not all that interesting. I just wanted to get across the point of kind of stuffing a longer history into a Markov framework. Okay, so question 1 here is actually, I think I can simplify writing these questions. They're all going to start the same way. So given that the last 2 widgets were defective, the last 2 widgets to come off the line are or were defective. So that's going to be the beginning of 3 different questions. So question 1, what is the probability that the next one is good. And I'm sure a bunch of you are groaning right now. This is something that is simply read off the matrix. So this means we've gone defective, defective to good. So we go from defective, defective to defective good, and we find that number defective, defective, defective good right here. So the answer is 0.6. I'm going to do something slightly more interesting now. In my next question, sorry, I want to keep going. If we were in a classroom, right, we'd have several boards, and I can leave this up there and move to the next one. Okay, there's my matrix again. So question 2, again, they all start with defective, defective. And so now I want the probability. What is the probability that the next 2 are good? So again, they start defective, defective. So we're looking at defective, defective, good, good. And so that is really 2 transitions from defective, defective to defective, good to good, good. Now it's not, well, I'll finish this, but I bet I know what some of you are thinking. Let's just do this. The transitions of a Markov chain are independent because once you know where you go depends only on where you are, and now where you go depends only on where you are, and those get multiplied. So I am going to look at the defective, defective to defective good entry, which is 0.6, and then the defective good to good, good entry, which is 0.85. So the answer is 0.6 times 0.85, which is 0.51, I think. So before I ask if there's any questions, the thing I thought that some of you might be thinking is, should we square the matrix? And the answer is no and kind of yes. So the reason the answer is no is because squaring the matrix gives you 2-step transition probabilities. So it's like going from where you are at time 0 all the way to time 2 and skipping something. And here we're not skipping anything. So that's why I didn't square the matrix. However, in this particular example, there happens to be only one way to go from defective, defective to good, good in 2 steps. Because there is only one way to go from defective, defective to good, good in 2 steps, yeah, I could square the matrix and take the defective, defective to good, good entry. But in general, there may be, multiple things you can put in here that will start you here and end you here. So I didn't square the matrix because I was not actually skipping a time step. I know what I want in the middle, but in this case, that actually is locked in once I know what I want over here and over here. So I have one more question going with this problem. Question 3, again, starting defective, defective. I want to know what is the probability of at least one defective in the next 3 widgets. So it looks like this: defective, defective, and then there's 3 things. And we want to know the probability, oh, sorry, that had some lag. The probability there's at least one defective in there. So one thing we can do is start writing out all possibilities. But in this particular case, it's easier to say that we could look at the complement of the event, right? So the complement is all good in the next 3. And that's going to be a lot easier to look at. So the probability of the thing we want, this is This is what I wrote for question 3, is 1 minus the probability. My notation is getting worse. Defective, defective, good, 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 which really means we're going from defective, defective to defective, good, to good, good, to good, good. Okay, so the answer here is 1 minus, and then defective, defective to defective, good is 0.6. Defective, good to good, good is 0.85. And good, good to good, good is 0.95. I'm not sure what that is, but that's a number. Which, by the way, on homework or exams, you can leave an answer like this. I don't care if you simplify anything, really. So that's it for longer history. I said there are some things you can do, but it tends to be a kind of brutish approach. So next up, we're going into the section in the notes called classification of states. And I am going to share a different screen with you. Okay, so here I have a matrix. I actually took this from, and please let me know if you can't see it. I took it from homework 1, a problem there. And I think the states were 0, 1, and 2, but because this is R, because R labeled them 1, 2, and 3, let's just say the states are 1, 2, and 3. So for example, the probability you go from state 1 to state 3 is 0.1. And you don't really have to write this down. You don't have to write anything down, but definitely not this. So I am gonna square the matrix. That's just how you, oh no. Since I did this, I redefined the matrix. I don't want to take the time to redo that matrix. So I'm gonna pull up the notes where I have another example. Okay, so I'm gonna stop sharing that and go into the notes just because I don't want to rewrite this matrix over and over again. I'm sure you don't want to see it either. So this is the beginning of section 2.5 called classification of states. This isn't nearly as interesting an example as the one I was about to show you. So what I have, I don't know if you could see my mouse, I'll keep it moving to draw your eye. I have a matrix on 2 states, a transition matrix, and then I just decided to go decimals. And I squared it, so that this is the matrix of 2-step transitions. And I cubed it, and this is the matrix of 3-step transitions. And I took it to the 4th power, and this is the matrix of 4-step transitions, and so on. Let's jump down to the 6th power. Right down here is the matrix of 6 time-step transitions. And what do you see? You see the column settling down to constants. You see this number is 0.65217, and the number below it is 0.65217 if you rounded it, but getting close. And this number and this number are approaching the same thing. And I thought the example I was trying to bring up in R was far more interesting because it was going to take a lot longer for this to happen because it doesn't always happen this fast. But if this happens, so if you take powers of the matrix and then it makes everything in each column a constant, then what you're seeing is, this is the probability you go from 0 to 0 in 6 time steps. And this is the probability you go from 1 to 0 in 6 time steps. And it looks similar, and it's going to get closer and closer as I take more powers. What this is saying is for this Markov chain, if you let it run forever and reach a sort of equilibrium, the probability you'll be in state 0 is approximately this 0.652 thing. And it doesn't matter where you started. So if the Markov chain runs long enough, it can forget where it started completely. And again, in the end, so if you imagine running this for an infinite amount of time, no matter where you start, in the end, you'll find yourself at state 0 with approximately 0.6522 probability, and at state 1 with the rest of the probability. So I call this, well, not just me, this is called a limiting distribution for the Markov chain, and they don't always exist. You know, the Markov chains do not have to settle down like this. And so we're going to talk a lot more about the idea of a limiting distribution. I'm sort of just going to leave that right there. The reason I bring this up now is because we're going to start to look at a bunch of definitions of things that just may look a little dry and totally abstract. The reason for them is because we have a group of theorems coming up that tell you things like when the limiting distribution exists. So you can say, if your Markov chain has this property and this property, then this limit will exist. And so I need to define a bunch of things to define those properties to state those theorems. This whole time I should have been working on the screen share. Okay, so we're in a section that I'm calling classification of states of a Markov chain, which again is just a bunch of definitions and stuff, but we're trying to be able to state some theorems about when that limit will exist and other things. So the first definition is, we say that state I, I'll not use quotes, let me use a color. State I can be reached from, or another way we say this is accessible from, or by, from, I guess. Okay, I could save this definition, but I don't want to. I want to change that I to a J. Sorry about that, because I really want the I to be the starting point. So state J can be reached from, that's not for, that's from state J if the probability of going from I to J in n time steps, now that's not that probability to the nth power, that's the ijth entry of the nth power of the matrix. If this is strictly positive for some n, non-negative integer n, so this should be an I. State J can be reached from I, meaning you can go from I to J, thank you for fixing that, in some number of steps with positive probability. And it doesn't mean you need to be able to go in one step. So if the ijth entry of your matrix is 0, that doesn't mean you can't reach J from I. It just doesn't happen in one step. But you can reach it if you can find some integer n such that this probability is positive. And note that that's not what I want to underline, n equals 0 is actually allowed. This is a convenience, much like defining 0 factorial to be 1 is a convenience. Because of this, state I can always be reached from itself because of that definition, because you could not move any time steps. So it can always be reached from itself, only because we're putting 0 in here, and it's only to make things work out nicely in some upcoming sums. So you might have like state I in your matrix. Let me just make this an actual number. So like 0, 1, 2, 3, 4. You may have that, if you're at state 3, you will immediately go to state 0. And then you might have no other way to get to state 3. Okay, I don't know what I was thinking, trying to write part of this matrix. That's supposed to be a column of zeros. So here, if you start at 3, you immediately leave, and there's no other way to get to 3. I know those look like dots, but those are zeros. So you're not going to get to 3, even if you start at 3. But because of this little blip in the definition, state 3 can be reached from state 3. Okay, we don't want to write that all out like that. So we write this as I and then an arrow to J. So my next definition is, and I'm sure you can see this coming, is about the communication between states. So if I can go to J, I'm going to start saying it that way because the can be reached by has screwed up the order for me twice now. So if you can go from I to J and you can go from J to I, then states I and J are said to communicate. And that was supposed to be yellow. And we write IJ with like a double arrow between them. So this is our notation, I, arrow, arrow, J. If you're reading Durrett, which is one of the two optional textbooks that I linked, it's going to look like his definition is different. It turns out it's the same, but I can't tell you why it's the same until I say a few more things. Okay, so communication is an equivalence relation, which you may or may not have seen in some other kind of math class, usually in a more like abstract algebra class, equivalence relation. But I'm going to define what this is. So it is some sort of binary relation where you compare two things. And to be an equivalence relation, you need three properties, and they have names. So the first is the reflexive property. So communication is reflexive, and that means that I communicates with itself. And I wouldn't be too sure of that, except that's how we defined it. So we can take n to be 0. The definition of equivalence relation is that you have these three properties. The second one is it is symmetric, right? And that means that if I communicates with J, then J communicates with I. And this is totally by definition because communication meant that we can get from one to another. So there's really no proving it's symmetric. And the final thing is that it is a transitive relationship. And so this means that if I communicates with J and J communicates with K, then I communicates with K. This one, while maybe obvious, needs some proving, but this is the transitive property of this relation. And so let's prove this one. I communicates with J and J communicates with K implies there exist some integers such that we can move between these guys. So there exist integers n and m such that, and more integers actually. So such that I can go from I to J with some positive probability in some n steps, and I can go from J to K in m steps with positive probability. So there's also two more integers of interest, and that is going backwards. So really, I'm looking at part of the definition of this, and I'm only looking in one direction right now. Right, so we need to show that there is some integer that we can put up in this exponent where we can go from I to K in some number of steps with positive probability. So I'm going to consider the probability of going from I to K in n plus m steps. And I'm going to use the Chapman-Kolmogorov equation. So that's for Chapman-Kolmogorov. So this is going to be the sum over some intermediate state. I'm going to call it L. I always make that sort of script because, I don't know, my line can look like a 1 or something like that. So over all L in the state space, the probability you go from I to L in n time steps use any letter you want. We're not going to reuse this equation. And then L to K in M time steps. Chapman-Kolmogorov says we can do that. But the L is running over the whole state space, so it will hit J. And so this is greater than or equal to Pij in N steps times Pjk in M steps, because this is just one of many terms in here. All the other terms could be 0, but I know that at least this is in there, and this is positive. Let me write that. It is positive. So I took only one term of interest and threw out the others, but here's what we have. I can go from I to K in N plus M steps with positive probability. So that means I can go from I to K, or K can be reached from I. And then we have to do the other direction, which I won't drag you through. So also need to show that from K you can go to I. And those aren't necessarily going to use the same integers, so 2 more numbers of steps. But we've proven it. So if you've heard of an equivalence relation, you might suspect what's coming next. Equivalence relations equivalence relations allow us to break sets of things, numbers, objects, into what are known as equivalence classes. And you put numbers or objects into the same class if they have the equivalence relation, which right now is communication. Let me write that down. That just sounded like a bunch of words. So N equivalence relation, that's an R, doesn't look like it, but allows us to partition the states or the state space. Technically, I need an equivalence relation on the states. I probably should have put that in up here. But it allows us to partition the state space into what are known as equivalence classes. And more specifically, since we're basically saying that I and J are somehow equivalent, they're not if they communicate. So these classes are known specifically in what we're doing as communication classes. So here's the important thing. 2 states communicate if, I'm sorry, 2 states that communicate are put into the same class. That's how we build them. 2 states that communicate get put into the same class. And I do have a lot to say about moving between classes, but I think this might be clarified with, or it might clear up a lot of things to look at an example. So in my example, I have a kind of large state space for us. It is 0, 1, 2, 3, 4, and 5. And I'm about to write a huge transition matrix. It is not really important that you get these numbers. It's only important that you know where transitions are possible. So like that you have zeros in the same place that I have zeros, and non-zeros in the same place that, I do not have zeros. But if you're ready and don't want to keep looking up at the screen, across the first row, I have 2/5, 0, 3/5, and then the rest are 0. For the 1 row, I have 0, 1/2, 0, 1/2, 0, and 0. For the 2 row, I have 2/3. This is a pretty sparse one, but only to make this an easy example to do quickly. 2/3, 0, 1/3, 0, 0, 0. In the 3 row, I have 0, 1/5, 0, let's say I need to come up with a number, 4/5, 0, 0. And the 4th row, I'm going to let 4 go directly to state 0 and 1 and 4 and 5. And I'm going to put equal probabilities there. So 1/4, 1/4, 0, 0, 1/4, 1/4. And finally, I'm going to put like, I don't know, just straight 1/6 across the entire 5 row. I say that weird, right? Because it's not the 5th row, it's the 6th row, but it's the row labeled by 5. And so what I want us to do here is to find all communication classes and separate them into sets. Keep as much of this matrix as I can. So I'm going to put a bracket here. I'm going to start a communication class, and I'm going to put in just the first state. So I'm going to look at 0. What does it communicate with? It already communicates with 0, so I don't really care that I can go from 0 to 0. By definition, 0 communicates with itself. I can go from 0 to 2, but they don't necessarily communicate unless I can get back. But here you can see that I can get back. So I can go from 0 to 2 and from 2 to 0, and it happens to be in one step each, but that is not required. So I'm going to put 0 and 2 in the same communication class. It's hard to see directly what else it's going to go to, but maybe I can take several steps to get to something else. Let's look at state 1. State 1, I can go to 1, which is irrelevant. And from state 1, I can go to 3. And from 3, I can go to 1. Actually, the way I did this, you can see like a little block matrix here. Ignore that 1/2. 0 and 2 only go to 0 and 2 and nothing else. 0 cannot go anywhere else. And 2 cannot go anywhere else. So I won't drag you through these. I'll let you think about them on your own. But actually, this closes the communication class. And if you look at the 1 to 1, 1 to 3, 3 to 1, and 3 to 3, you have a little block matrix there if you ignored the rest. 1 and 3 definitely communicate. And it's a bad example that it happens in one step, but I wanted to write something simple and really sparse. You don't have to be able to move in one step. 4, state 4. Actually, I know I cannot get to state 4. Look at these zeros. I can't get there from state 0, 1, 2, or 3. And because from stage 0, 1, 2, or 3, I also can't get to 5, there's actually no way to get to 4 from those states. It starts its own class. And from state 4, yes, I can go from 4 to 0, but then I cannot get back in any number of steps. Because from 0, I can only go to 2, and from 2, I can only go to 0. So then I'll be spinning around between 0 and 2. And let me just put this out of its misery. I can go from 4 to 5, and I can go from 5 to 4. Again, these happen to be one-step possibilities. It does not have to be in one step. But I've made 3 classes, and everything in here communicates, everything in here communicates, and everything in here communicates. And you can move from one class to another, but if you can, you cannot come back. So I don't know if you can see me in the corner of your screen, but if this is a collection of states, I've got a bunch of states in a set over here and a bunch of arrows, I can move between them. And this is a collection, another class, bunch of arrows. If I can go from one class to the other, then there's no way to get back, because that would mean that for any state in here, I can go where I have to go until I get to that exit arrow, and then go where I have to go until I can get to that exit arrow. And they would all communicate. They all would have been one class. So they wouldn't have been separate classes to begin with. So you can move from one class to another, but then you cannot move back. And I will write that down. But before I do that, I want to say that I want to define something. So these states, 0 and 2 are what we call recurrent states. Not sure I'll get to it today. I have a formal definition coming up, but a recurrent state is one that you will come back to eventually. It could take you a very long time, but you will come back. They recur. So it's actually a probability 1 statement, and I'll write that down eventually. You're going to come back with probability 1. We'll come back starting at either 1 with probability 1. In fact, there's no way out of this class. There's no 2 to 4. If there was, then 0 and 2 would not be recurrent states because I could disappear, never to return again. Otherwise, they would have made the same class. Okay, states in this particular example, states 1 and 3, because of that little block matrix thing given by these circles, I can only go from 1 to 3 and 3 to 1 and nowhere else. States 1 and 3 are also recurrent. And states 4 and 5 have a possibility of escape. So states 4 and 5 are said to be transient states. And a transient state is there is a positive probability to escape. So starting from state 4, you may go back to 4, back to 4, over to 5, back to 4, over to 5, 5, 5, 5, 4. You may spin around for a long time in there, but eventually there is an escape. So there is a positive probability to escape 4 and 5, never to return again. We are going to prove next time that recurrence and transience are what everyone calls class properties. And that we have a lot of properties in Markov chains that if a state has a some property of interest, like recurrence, and it communicates with another state, the other state has that same property. So what I'm trying to say is that if you have things communicating, then they either are both transient or both recurrent. And we can use these words, recurrence and transience, on the classes. So this class of states is said to be recurrent, and this class of states is said to be recurrent, and this one is said to be transient because from 4 and 5, you can go back to 0, and then you won't get back. So recurrence and transience applies to states and classes. And so we are on our way to that limiting distribution thing. One theorem that's going to give us a nice limiting distribution, and this is not necessary, only sufficient, is that the chain be irreducible. And that means that you can't break it into separate classes. It's just one big communication class. But I'm out of time. We're going to do that in person next time on Markov chains. So thank you.